So in the previous class, we had derived the equation for the propagation of the TM waves, and we had derived an equation for Ez component because there will be no H component, correct? And substitution of this Ez in the equations of other components, correct? Such as Ex, Ey, Hx and Hy we are supposed to find out. Okay, so that's what is the important part here, which we had not done earlier. Now I'll give you the answers, right? Which equation you are supposed to substitute and what answer you get. Okay, so right, so this implies, I'll directly write. So what is the equation for Ex, the X component of electric field? In the previous derivation, we had obtained this equation, minus gamma divided by h square into partial derivative of the z component of electric field with respect to x minus j omega mu divided by h square dou E z divided by dou y. Okay, this is the equation. So what we do, we directly substitute. That's all, right? So if you see in the above equation, right, we have the sign of something into x, sign of something into y. So both derivations we can do. Correct? Okay, I think I made one small mistake. Let me correct that. So the second component is not Ez, it is Hz. Please verify once. Okay, so this component is not Ez, it is Hz. Correct? Dou Hz. So actually Hz is not there at all, right? For a TM wave, correct? I'll just write here. Tm implies Hz equal to 0. So I just have to write this part, that's all. I don't have to do the second half because Hz equal to 0. But I just wrote the complete equation for our reference, okay? Out of which I'm substituting only for Ez. So Ez is in equation number 14, right? Which I need to differentiate with respect to only x, dou Ez by dou x. So after doing that, we get the following equation, okay? So that is minus gamma by h square. There is a constant c, magnitude, sine of m pi by a into x. When you differentiate, the m pi by a comes out, all right, into there is a sine component that's going to become the cos component. Okay, so cos of m pi x by a, because differentiation happens only with respect to x. Okay, so m pi by a times x. The other component, the y term, remains as it is because it is a constant. Okay, so that is sine of n pi divided by b times y. So exponential term remains as it is because, right, it depends on the time t and the z component, okay, z axis. So it's a constant for our differentiation. So j omega t minus it's gamma z. All right, so that is the equation for Ex. Very similar to that, but now we need to substitute this for the in the equation of Ey. So recall the equation for Ey was minus gamma divided by h square. It is dou Ez by dou y plus j omega mu by h square, partial derivative of the z component of magnetic field with respect to x. Anyway, hz is not there, so we'll substitute only for the first part, that is dou Ez by dou y. So after the substitution, I'm going to get this gamma by h square into the constant c, right, pi n divided by p sine of m pi x by a. Sine becomes cos. This is n pi y divided by b into e to the power j omega t minus gamma z. So that's the equation for electric field in y-axis along the y direction for Tm wave. Okay, so Ex Ui over. Next, our intention is to calculate the Hx. Let's look at the equation for Hx, which we had derived in the first case. So this is minus gamma by h square dou hz divided by dou x plus j omega epsilon divided by h square dou ez by dou y. So only this part is what we need to calculate. Other part is 0, right? So because of that, we have j omega epsilon divided by h square constant c. Differentiation is with respect to y. So the coefficient of y inside the cos comes, inside the sine comes out. Okay, so that is n pi divided by b. We had a sine of x component which remains as it is, sine of m pi x divided by a into, there was another sine component that becomes cos. Okay, this is n pi y divided by v into e to the power j omega t minus gamma times z is the equation of x component of magnetic field. Similarly, finally, we need to calculate the h component magnetic field along the y-axis. So the equation to be used is minus gamma divided by h square dou h z by dou y plus j omega epsilon divided by h square. This is dou ez by dou x. So upon substitution of the equation number 13 over here, equation number 14 over here, we are going to get, again, the first term is 0, hz is 0. So we have j omega epsilon divided by h square c times m pi by a cos m pi x by a, because differentiation is with respect to x and x, y is a constant, so the second term is as it is, sine of, this is n pi y by b into e to the power j omega t minus gamma z. Okay, so all the required components, all the 4 required components we have calculated, right? That represents the complete electric and magnetic fields for TM wave. Okay, now the important aspect is that, right, by substituting different values of m and n, you can see that there are m and n in each and every equation we have written so far, right? Substitution of the values of m and n, right? What are m and n, right? They are the integers, right? For which we satisfy some of the conditions in our equation. You see, b is equal to m pi by a, so that the b into a is equal to 0, right? Some of the components will become 0 whenever the m takes a value, integer value. Similarly, when we substitute n as some integer value, some other components in our derivations become equal to 0. That's why we use the specific m and n, right? So whenever we substitute the various m and n values, right, we get the Tm modes. Okay, so this is called as Tm modes. Whatever m and n we substitute, and we get specific waveforms. Okay, specific waveforms inside the rectangular waveguide. We call them as Tm of mn, right? So this is depending upon the m comma n values. We say that the Tm m comma n mode of propagation inside the rectangular waveguide. So let us see, right, what are the modes. Let us try to substitute both m and n as a 0, 0. Okay, so the first mode we are going to look is Tm 0, comma 0. This means m becomes equal to 0 and n is also going to be equal to 0. This is what I need to check what happens. What are the various fields we are going to get, right? Let's check. Let's go back to the equations of various. Okay, so check whether when I substitute m and n 0, what happens to ex. I can see that there is a m here. So sorry, I marked a pi. So it's this m we are talking about. So as soon as this m becomes equal to 0, ex is 0. There is no ex. All right. So I proceed further. Check for ey. There is n outside. In a sense, right? N becomes 0 means the whole term becomes equal to 0. So no ex, no ey. Let's proceed further. Check whether you are going to get a term for hx. N is 0, it vanishes. Right? Again, m is 0, hy is also vanishing. There is no field component that's going to exist. So Tm 0, comma 0 means all the fields. I can directly write. In this case, I don't have Ex equal to Ey equal to Hx equal to Hy equal to 0. That means, right, this mode Tm00, right, can not exist. It cannot exist inside the rectangular waveguide. So maybe a short question if I want to ask, I can definitely ask whether in a rectangular waveguide I can have Tm maybe 1, 0, right? I can simply ask like that. Okay, so like that. Now you verify whether you can have the Tm 0, 1. M is equal to 0, n equal to 1. So m 0 and n equal to 1. Right? If all the fields vanish, then I can say that no, it cannot. Right? Any one of the mode exists means yes, that can propagate. So m0, first thing vanishes. I'll go to the second one. Second, also I have a sign of m into something. So sign 0 is 0. That's also not going to exist. So anyway, right, again sign mx, that's 0. In the hy also m is outside. As soon as you put m is 0, it's 0. So right, this means here I'll write all field components vanish. All this implies it cannot exist inside the rectangular waveguide. Right? Similarly, I can also verify Tm10 for the same reason, right? It cannot exist. Moving further, just check Tm11. When I write a Tm11, I can say that m is 1, n is also 1. So if you check the equations for Ex, right, a constant, pi into 1 by a, cos of 1 into pi by a into x, sine of 1 into pi by b into y, into yes, ex exists, right? Check for ey also will exist. We'll check the hx, right? None of the terms are 0. You will get hx as well as hy. So all the field components do exist here, right? We can write the m and n values as 1. So since all the 4 components exist, all the 4, I can write as the same, all the 4 field components exist. So Tm11 exists, right? And all the higher values of m comma n more than 1, whichever you substitute will exist, right? No. Okay, so okay, this mode can exist, right? So for m greater than or equal to 1 and n greater than or equal to 1 means all higher modes exist inside a rectangular waveguide. All right, now uh, let's look at the most widely or most common application of a rectangular waveguide. That is going to be a high pass filter, right? Whenever I want to send a frequency greater than a specific frequency, right, all the signals can be passed, right, by using what is called as a rectangular waveguide. So its common application is as a high pass filter. So that means I need to know what is the cutoff frequency of rectangular waveguide. So we have two equations. One equation is for the calculation of the frequency, right? I'll write Fc is equal to, this is the equation, C divided by 2 times, this is M by A whole square plus N by B whole square raised to the power half. It's whole root of. Okay, so this implies I can also calculate the lambda cutoff wavelength. Lambda c, basically it is simply c divided by cutoff frequency. So c already is there, the c is going to get cancelled. Okay, so we can write this as, so this is 2 divided by m by a whole square plus n by b whole square, everything under root. Right, this can actually be further simplified and we can I can give you a simplified answer. This is lambda c is equal to, after simplification we can come to this, okay, 2ab divided by root of, this is m square b square plus n square a square. So m and n are the constants that depending upon which mode you are trying to propagate. Okay, so that's how we can calculate the cutoff frequency. Right. Then we have another important term that is related to the waveguide, which is called as a guided wavelength. Right. So here, let's try to denote this first. It is denoted as lambda g of a rectangular waveguide. So it's the distance traveled by the wave in order to undergo a phase shift of 2 pi radians. Okay. So, okay, we can define this first. Is defined as the distance traveled by any wave in order to undergo a phase shift of 2 pi radians. Okay, so this is the normal, the lambda g, that can be calculated as the 2 pi divided by beta. Okay, but there is another important relationship which we need to remember, that is 1 divided by the lambda g is equal to, sorry, it's a square. 1 divided by lambda g square equal to 1 divided by lambda naught square plus 1 divided by lambda c square. So where the lambda naught is the free space wavelength. If the same wave is not propagating inside the waveguide, but it is propagating in the free space, then whatever is the wavelength of that in free space is called as a free space wavelength. Okay, that is lambda naught, and I also have an equation for lambda g we wrote, right? Okay, we know the lambda c, right? It's the cutoff. Okay, so let me write the lambda c is the cutoff wave length. Right. So further, this equation, whatever we have above, right, the three terms can actually be simplified and written. You can write it as it is equal to lambda naught divided by root of 1 minus lambda naught by lambda c the whole square. Again, just mathematics, we have to do some maths over there to get this. All right, then we have the another important term that is called as the phase velocity. So phase velocity, it's denoted by Vt. So we just now have seen that the wave propagates in the waveguide whenever the guided wavelength is lambda g, right? And the free space wavelength becomes lambda naught. With that representation, we know that it propagates. Now the Vp, or it's the phase velocity, it's like it's the rate at which the wave changes its phase in terms of the guided wavelength, right? So that's what is the definition of this. So we'll try to write that it's the rate at which the wave changes its phase. Its phase is what is a measurement, right? So we can try to write the Vp equation as the omega divided by beta. Okay, where how do you calculate omega? Omega is equal to 2 pi into f, and the beta is equal to, if you want to use it, it's 2 pi divided by lambda g. All right. With respect to the phase velocity, we have another term coming into picture. All right. So that term is called as the group velocity. So let's call the group velocity as Vg. So if we want to define the Vg group velocity, it is the rate at which the wave propagates through the waveguide. It's actually the normal velocity term itself. Okay, so I can write the rate at which the wave propagates through the waveguide. So it's Vg is equal to d omega by d beta. The rate of change of angular velocity omega with respect to beta. Okay, so that's how we calculate, right, the equations. Right. So let me check whether I can give any other equations as well. Right. These are the definitions. Now let me try to give the equations in other terms. right? So that will be uh, okay, right? The other standard equations we are going to use, maybe just to solve the problems, will be like this. If you want to calculate the VP, we can use one equation is C divided by under root 1 minus FC divided by F the whole square, or this is also equal to, if at all I want to write in terms of the lambda values, okay, so that will be this equation we have seen. This is 1 minus the lambda divided by lambda C the whole square. So where in the first equation, the F represents the current frequency, whatever is the operating frequency of the wave. FC is the cutoff frequency. Okay. So phase velocity, yeah. So the phase velocity Vp depends upon numerator. You can see C, right, in both equations C, right. So it is the velocity of light in free space. Okay, divided by root of 1 minus, first equation will have Fc by F whole square. In that, right, the Fc is the cutoff frequency of that wave. We already have an equation to calculate that. And F is the current frequency. Okay, in the sense, cutoff frequency is 2 gigahertz, but right now I'm sending a wave which is 3 gigahertz. So you see Fc by F becomes 2 by 3. Is it okay? So similarly, the lambda is the current lambda value. Lambda C is the cutoff value of the lambda. Okay. So I can use these equations whenever required. Is it okay? Right. Also, let's try to write the other equations, right? That is for group velocity. Right. If at all you want to calculate the group velocity, that is Vg is equal to first equation. One of the equation I'll try to give in terms of okay. Right. So one equation is in terms of the lambda values. Okay. So C into square root of, this is 1 minus lambda by lambda C the whole square. Okay. That's first equation. And also the other equation will be C times square root of 1 minus Fc by F the whole square. Okay, so from these two equations, we can come to another very important equation, that is Vp into Vg is equal to C squared, right? So multiply and you will get that, right? Any two terms you multiply, you can see that if I multiply these two, right, I can see that these terms will cancel. So C into C, C squared, right? So I get that equation, which is also a very useful equation, okay, to solve the problems required uh, whenever we want to, right, uh, apply them to the numericals. Is it okay? Do you have any doubt with this? All right. So all right. So let's move further, right? Now, in order to represent the TE mode, right? We have seen the TM mode. Let's move ahead and represent the TE waves. Transverse electric waves inside the rectangular wave guides. Okay. Now, so what do you mean by transverse electric wave? What do you mean by that? Electric field is not there along the z-axis. So Ez is equal to 0, right? Ez is equal to 0. This means the Hz is not equal to 0. For energy transmission, I cannot have both of them 0. If both of them 0, it is TEM mode, right? Already we have. Right. So what we'll do, we'll start from the wave equation. All right. So, but the of, let's say, the transverse electric wave, right? How do you write that? This is nothing but, already we have seen, so L square Hz is equal to minus omega square it's mu into epsilon into Hz. Okay, it's called as a Helmholtz equation. Already we know that, we have studied this. So I'm directly using it. So what is a del square? Expand the del square. It is a partial differentiation. Okay, so dou square Hz by dou x square plus dou square Hz divided by dou y square plus dou square Hz divided by dou z square. So recall the derivation we did for TE mode, sorry, TM mode, okay, earlier. Same derivation, but now it is in terms of H component. All right. Should be equal to, right? On this side, we don't make any changes. We'll simply write it as equal to minus of omega square mu epsilon times Hz. Okay, so we know, right? If at all your wave is propagating along the z-axis, then the dou square by dou z square is a gamma square, right? I'll just write here dou square by dou z square is the gamma square, right? Same thing we have applied even in the previous derivation. So I can update my equation in the following fashion. So dou square Hz by dou x square dou square Hz by dou y square. You see the dou square by dou z square is gamma square. Okay. And on the right hand side, I have minus omega square mu epsilon. That I will bring it to the left side. Minus becomes plus, and then I take the Hz common. So what do you have? You have gamma square coming from the first term, and the minus omega square becomes plus omega square mu times epsilon. This into Hz. Okay, right hand side becomes equal to 0. I simply saved one step, but I also know that this term is nothing but the h square. Correct? So my final equation becomes like this. So this implies dou square Hz by dou x square plus dou square Hz by dou y square plus h, uh, h square into capital Hz is equal to 0. Is it okay? So it's the partial differential equation. Let's call this as equation number 1. Right. So if you recall our previous derivation, once I got a second order differential equation like this, right, I am going to assume the answer, right? So assuming the solution as, say, what is the solution? Solution should be Hz. Which value of Hz or which equation of Hz solves this equation? That's what is a solution, right? So Hz is equal to, let's assume capital X into capital Y, right? So where, let's call this is 2, where, recall, what is a characteristic of X and what's the characteristic of Y we are expecting? Its X should be a pure function, correct, of X only, right? Of Y. Perfect. This is because, recall mathematics behind this. We are calling this, that we are going to apply a method of solution of a differential equation that is called as separation of the variables, right? I should be properly separate the, I should be able to generate a function Hz in such a way that the Hz can be written as a product, one term containing only x, another term containing only y. And we could do that in the previous case. We could get one term in terms of only x, something like a sine of m pi x by a. You see, that is a x term. Similarly, we had a second term coming, that is sine of n pi by b into y. Correct? So you can see that, right? So that's what happened. Right. Now, let us try to substitute this, right, in the above equation for hz, right? So we'll skip one step because we already have done that. So I'll skip a step, right? So this implies the equation number 1 becomes, so I have hz equal to x by x into y. What is dou square hz by dou x square? That is simply y into, right? It's a pure derivative now. So d square x by dx square. Are you okay with this, or do you want explanation? You are able to recall, right? We had done this, right? Okay, so plus x into, this is d square capital Y divided by d small y square plus h square into capital X into capital Y equal to 0. If you remember, we divided this equation by capital X, Y later, so that I got a proper terms in terms of X. Now you see X and Y are mixed here. I don't want them. Okay, I just want them to be separated. So you can see when you divide by xy throughout, this becomes 1 divided by capital X into d square capital X by d small x square plus 1 divided by y d square capital Y by d small y square plus h square is equal to 0, right? So I understand that this function has only y, correct? This has only x in it, right? Right. So recall the next step. What was the case? You try to substitute something for this. That is, let 1 by x d square x by d small x square, you called this as minus b square. Similarly, the term containing y, so d square capital Y by dy square, we call this as minus a square, right? Where a and b are constants, so minus a square minus b square also constants. We got some constants over here. So this implies in the above equation becomes, right? So yes, perfect. So I can write, therefore the h square can be written as the a square plus b square, right? So again, the solution of this kind of equations can be directly obtained by using the variable separation method. Okay, so by using the separation of variables, right, we get the solution. The solution will be of the following form. So this will be one constant into cos bx plus another constant into sine bx. It's in terms of x only. You can see that the capital X is a term which contains only small x. Similarly, y is, let's write c3 cos ay plus c4 sine ay. I hope you are fine with till here. Okay, so this implies, what's your final answer? That implies, right, the complete solution hz is equal to its capital X into y. So that means hz can be directly written in the following format, right? So that is c1 cos bx plus c2 sine bx, first term, multiply this with the second term, that is a c3 cos ay plus c4 into sine a, right? With the c1, c2, c3, c4 are the constants, right, to be evaluated by applying the boundary conditions. I hope you are fine till here. Let's proceed. So now our intention is that I need to look at the boundary conditions. Right. Recall the same waveguide which we had written earlier, right? What is a T wave representing? Let's write the T wave once again, right? TE wave means what? Ez equal to 0. Okay, but we have other components along x and y direction. Ez 0, but we have other components along x and y directions. Okay, now you see, we will consider the same old uh, diagram once again. Okay, let me go back. I'll show you this so that, yeah, this one. Okay, recall. So the width is B, breadth is A. A is measured along x-axis, B is measured along y-axis. So that I can input the wave from this side. It travels along the z-axis and comes out from the other side. Okay, that's the hollow part, right? Within the hollow part of or hollow volume that resides inside my waveguide, the wave will propagate. Okay, so now the wave is such a way that Ez, there is no Z component of electric field, but Hz will exist. Right. Now, what is a condition that you're going to apply? Immediately at the boundary, right? Or outside the boundary, you don't have Ex, you don't have Ey. Correct? You don't have Ey, and it's simply because the reason is that it acts like a short for you. Recall the condition we discussed, right? It's like everything is connected. So for electricity, if your view is in terms of electric field, it's a short circuit, right? Short circuit means 0. Are you okay? Yes. So boundary condition, I'll write in general first, then we'll apply the specific boundary conditions. Okay. So this implies, uh, fine. So Ex equal to 0, where in which parts Ex equal to 0? It's along the bottom and the top surface. Okay. Along bottom and the top surfaces of the waveguide. Is it okay? Similarly, I can say that Ey becomes equal to 0. No y component along the left and the right surfaces. Are you okay? Of the waveguide. This is what I'm supposed to apply. Okay, now I'll split the two lines which I have written now. I'll split them into 4 boundary conditions. Okay, so this is first boundary condition. So I'm going to apply to the bottom surface. At the bottom surface, my condition is Ex equal to 0, right? What is the condition for the bottom plane or the lower surface of the waveguide? In the lower surface, no height, correct? So that is equal to y equal to 0. Okay, and x varies from 0 to a. Are you okay with this? No need to show the diagram again, right? Okay, so let me proceed further. Directly I'll write. So this is the second boundary condition. I'm going to apply this to the left side wall of the this one. Okay. So left side means it is EY. Okay. EY is 0. No Y component. At for the left side wall, right? The X becomes equal to 0. Okay.